So it's a deploy wave. Yeah, I've mentioned this before. So deploy wave. So what is a deploy wave? Before we talk about wave, do you know what is deploy wave? Have you heard of what is a wave? What type of wave we're talking about? This idea was put forward about 1925. Okay. So you mentioned the momentum, right? What is the formula for? If you don't know, if you're not, so what is the formula? Have you learned? What is wavelength formula? Lambda equal to what?
Frequency times lambda. Wavelength
Divide, yeah. So what is this has something to do with the Planck constant? Yes.
Oh, h over f.
No, divided by momentum. You mentioned. Can you see? So P here is momentum. Did you ask this question? There's momentum or particle. Can you see that? That is the formula. That is the original formula. Yeah. So the question is, what is a wave? So what type of wave? So we just highlighted this wave. So what we have learned very different wave. We have learned sound wave, water wave, right? Light wave, electromagnetic wave. Of course, electromagnetic wave is light is a part of electromagnetic wave. Okay. So that first, to understand this idea, you have to really understand what is a wave, right? So we have, and also what is momentum? Momentum is for the particle. Can you see? Oh, sorry, this is not P. They should be. Wait a moment. Multiply V for velocity. M multiply velocity. Do you remember the momentum? Momentum. It's the momentum. Momentum. When we send a collision, you see the two ball with when they collide to each other, right? Then we can introduce the momentum to describe the motion. In the same way as we use the velocity, you see. So momentum is a product, is a vector, right? Momentum is a vector. So, but why the momentum have anything to do with wavelength? That is a question. That is a question of this idea. This is a part of quantum mechanics. Can you see this velocity? And is mass. So if you got a product, you got a momentum. So basically, the Broglie wave is special. Okay, we have probably read several waves. Is what talking about the wave. Okay, I read what two. I put a table here. We got a particle. Okay, so first of all, we had a particle, like electron particle, and we got a wave. Okay. So we have studied many things. We have studied in particular, we have studied the light, right? Light has been studied as a wave. You agree? Yeah. For the light, we use electromagnetic wave. You agree? It's not mechanical wave, but electromagnetic wave. Of course, for the sound, do you know the sound? Sound is not wave, it's a mechanical wave. Can you see? Mechanical wave. So these are the how to describe this phenomena, light, and how about the atom? How do we describe that? Do we describe atom as wave? or particle?
Particle.
Yes, particle. Okay, so that is so we treated the mass as a ball. Can you see? We consider the atom as a ball, a solid ball, right? So we barely use the wave to describe the atom. So we're going to build this. We're going to build this table to understand the related idea. You see. Now, they just put them together. So basically, so this is a. So we put this two category. Another thing is electron. How about electron? What do you think electron? What does electron? How do we describe electron or proton, if you wish?
A particle.
It's a particle, right? It's even the point particle, right? Because so small, right? We just use a point particle, right? Point mass. We point mass. What is charged mass? Can you see? Like this model, can you see? For example, when we study the electron in to put it this way, can you draw a diagram? So when we start electron in a vacuum, right? Photoelectric effect, right? For example, but perhaps this time we just talk about the J.J. Thomson's experiment. What he did is a filament, okay? So you adjust the lamp, which makes that filament very hot. And this is a vacuum tube. Did the teacher do any experiment? Measurement?
No.
No, it's hard, right? It's vacuum. So what this experiment is that we could put this, we put ammeter here, okay? It's kind of connector of the electron. And then in addition, we apply the positive voltage here to accelerate that the electron, you see? So that is an experiment set up by J.J. Thomson, you see? And in this way, and the electron is negatively charged, right? Negatively charged. So this electron, right? So electron will be speed up because this filament getting very hot, like a lamp, right? So electron can move out around this filament. Because we have applied the electromagnetic force here, so electron will be experience a Coulomb force towards that direction. Okay, so and also there's no shortage of electron because the negative this is battery, the negative side is full of electrons, right? So electron will go just continuously. As a result, we will see electron spin over here, okay? So that we can see the current form, right? Yeah. But of course, current will go different direction, but electron will go that direction, right? So this is the J.J. Thomson experiment. The experiment in which he found electron for the first time. The teacher mentioned him?
No.
Oh, you have to know who's J.J. Thomson first, okay? So this is clear. We can actually use this model. We can use the force. Can you see this is the force? We can use the force acting on this particle. As a result, each electron can be described as a momentum as well. Can you see? Because it's moving, or you can say that they have carried a certain amount of kinetic energy. But the base, first of all, this is the momentum of electron. In other words, when we use the momentum to describe an object, in this case, it's electron, we imply we are using particle idea, okay? Actually, if I just categorize it, so anything on this side, so it's called this called a real object. Can you see? So this is a column. The first column is called real stuff. Okay, real object. Okay. On the other, this second column is called ideal model. Can you see? All of them. all of them, including particle and wave. Two types of model, you see, ideal, ideal model. Do you understand now? In physics, we don't study the real stuff. We use model to describe the real stuff, right? When we study the sound, we use a mechanical wave, right? Both wave model. So in this wave, we can talk about the crest and throat, right? We can also talk about, importantly, the wavelength. So the wavelength is wave property, right? However, the momentum is a particle property. So return to the de Broglie wavelength. So what does it mean? Can you tell me? So we are assume if, for example, we are studying atom. When we study atom, we can use ball or particle, right? So all these are all of them are models. You see, but these models are very accurate to describe the real stuff. Another thing is if you use the Newton's gravitational law, when you start Newton's gravitational law, right? And the force between the Earth and the Sun can be described by this can be described by this Newton's gravitational law. You see?
Yeah.
So basically, if we know the distance, but we don't study real Earth or real Sun. For example, when we calculate the force between these two objects, we don't pay attention to the detail. The force between these two, what we used is actually a point mass. Can you see? We use a dot to represent the sun. You see? And we also use a dot, the mathematical dot, to represent the Earth. Because Newton's law didn't give us not much detail. We cannot consider the mountain or house on the Earth, right? We just use the dot at the center. Can you see? Mass center to represent the position of two objects. In this way, we can measure the distance between these 2 points mathematically, right? Accurately. So that's why Newton said, well, the force, if you do so, the force can be written as this formula. Can you see? That is the mass of the sun. This is the mass of Earth. Do you remember this formula? That's actually gravitational law, right? And that is the distance. So in this way, we still use model. Can you see? We don't care we don't care the diameter of the sun or Earth. Okay, we don't consider whether this the sun is liquid or gas. We just consider that's a mathematical point. So in this case, we also use a particle model, right? So these point mass are all particle models. But this makes it clear. The momentum is the particle property. Can you see? Particle it's a particle like. Particle is built by real particle based on basic particle. It's a basic property, right? Oops. What did I do? It's hard to touch something. It's a particle property. Well, this wavelengths, the wavelength is wave property. Can you see? So why do we use it? Why do we mix them up? Do you know why? Why do we, in the one formula, why do we mix them up? Why do we mix the wave property and the particle property? That is a very abstract idea. For this idea, de Broglie got his Nobel Prize. He solved the big, very fundamental based question, answered a very fundamental question in physics during the 1920s. Now, if you haven't learned this part, I can tell you. So this wave is special. It's called matter wave. Have you said matter wave? It's called the matter wave. Not the sound wave, not the light wave. It's called a matter wave. It's a new idea. What does it mean? The matter? Matter could be a particle. Okay? Mass could be particle with mass. So what is mass? What is mass? What is matter? Mass is an object with mass. Okay, an object with mass. It could be electron as well. Do you agree? With mass.
Yeah.
By the way, does a photon has mass? Yes or no? By the way, before that, what happened to Einstein's the photon electric effect? Let me put this question this way. Apart from use wave model, any other model, did we use any particle model to describe the light, visible light?
Photons?
Yes, that's right. You see? That is very important. I'm going to fill this table. So photon is a particle model for light, okay? And which was responsible for Planck. A great physicist called Planck, okay? That is 1901, okay? Of course, Einstein uses the photon idea to explain the photon electric effect. So if you just pay attention to this part, so what does that mean? So basically, when we start light, we can, so far we have used either the wave model and the particle model. You understand? Because before Planck, everyone thought light is part of electromagnetic wave, right? Hence, light can be described the wave equation with wavelengths. However, Planck proposed that sometime we cannot explain. We have to use a particle model like a photon. So for this idea, by describing the light, you either use a wave or a particle model. Physicists had explained several important experimental observations at the beginning of the 20th century. So return to de Broglie. So I have given you a hint already. For the electron, since J.J. Thomson, we thought electron is a tiny particle like an atom, like a photon, like a proton, right? So therefore, that is what we have done so far. Just draw this diagram for you. So in the case of electron is real stuff. We use point mass, okay? Do you think something is missing? If you look at this table, do you think we miss something in this table?
A wave model for electrons and atoms.
Good idea. Good idea. That's right. So if you're born centuries earlier, you get a Nobel Prize. Yes. It's called the matter wave. Can you see? Matter wave is a model. Okay. Not matter wave is not necessarily real. Okay. Matter wave is just a model. And that model is called the matter wave. Okay. Both atom, or you can go for electron, you can for proton. Okay. It could be proton, neutron, all of these. You see, proton, and also when we study have you started new standard model? Not yet. You are going to start standard model.
Yeah.
All of these models can be described as a matter wave. Can you see? Matter is called a matter wave. And then mathematically, we use this symbol to describe this wave. It's called wave function. Can you see? Same wave. Okay. Have you heard of wave function?
As in like a sine function?
No. Oh, it could be sine function if it's a sine wave. Yes. In a special case, if it's a plane wave, it's a sine wave. Yes. But this psi, this called psi, this Greek letter psi, this letter is used as wave function. Okay. Actually, what is the quantum mechanics? Did the teacher tell you? Quantum mechanics is based on wave equations, right? Matter wave equation is called the Schrödinger wave. Now, the reason why this is why there's necessity, we have to add the matter wave model for matter, is that there's another very interesting experiment done by the J.J. Thomson's son. See, and what this is an experiment. So this is a experiment done in 1897. Okay. And the J.J. Thomson's son, you can call the J. Thomson Jr., right? Jr. And he found something very interesting. You see, do you remember the double slit experiment? Double slit experiment for the diffraction.
Yeah.
Yeah. I think you have studied the part, right? That's part of the wave. We study the wave property.
Yeah.
Yeah.
Where,
Yeah. So that's I just draw the diagram very quickly. So what we do is put the we put a screen outside on. We put a screen. Okay, we put a screen behind this double slit. This screen. Okay. And we let the wave come. You see. The wave, do you remember the wave? The wave, if we can use this straight line to represent called wave front. This is wave, this is sine wave, it's called plane wave. Plane wave. So in other words, you will see the crust. Can you see? You can just this wave. So this is a crest. Can you see the crest? Can you see? So therefore, the distance between these two is wavelength between each of these three wavefront is lambda. You see?
Yeah.
So that is how to describe the wave traveled. This is lambda. Can you see? It's called wavefront. So, but what happens is that this is called wavefront. The wavefront. What happened to my pen? Okay, what happens is that the wave will stop because of this block, except these two tiny holes here. Can you see? There are two tiny holes here. So according to Huygens principle, we can actually argue that after that, the wave became the spherical wave, not plane wave anymore. So that's how we draw the next moment. So that will be the wave will propagate in this way. Can you see? Can you see this part of sphere? This is a semi-sphere, right? And so does this side. This side also will move forward like this. Can you see that?
Yeah.
And so the difference is that at the beginning, the wave travel in one direction. Can you see? In this direction, the wave will travel in that direction. But after that double slit, wave will travel in all directions. Can you see? And so does this side. The wave will travel that direction. You see? So do you remember what would be the result on the screen?
It would.
You get bright and dark fringe. It's called a fringe, right?
Yeah.
Dark and bright fringe. So if you just use intensity, you got the brightest at the center. And after that, you will see this dark and bright periodically. Can you see? Dark, bright, dark, bright. So that what form is called diffraction? Can you see? It's called diffraction, right?
Yeah.
The diffraction or interference, if you wish. This is wave property of the two wave aided. However, when Thomson used the same experiment, but what Thomson used, he just used electron. He used the father's apparatus to generate electron. You see, because electron is a particle, right? Electron is a particle. If you put the electron as a beam, the travel in that direction, then you would expect only two electrons, only two positions allowed electron to pass. Can you see? One is this electron can reach this position, all right?
Yeah.
And this electron can go through the straight line and reach to this position, all right? After some time, you can accumulate a lot of electron on these two positions. Do you agree? And that is if we just use a particle model, if we just use electron to describe if we use a particle model to describe electron. But to his surprise, what he observed is nothing happened like this, all right? But they still got the pattern of the interference or diffraction. So that is challenging. So that is when that phenomenon that is nobody have done that experiment, okay? And by the way, this experiment was done after de Broglie put forward his formula or proposed his wavelength formula by de Broglie. Can you see that? Can you see that? Can you see the whole story now?
Yeah.
So basically, without when de Broglie looked at this the current study during 1920s, he noticed that we have used when we describe the light with a photon particle model, we make some progress, right? In other words, the real stuff called light can be described by either particle or wave. But de Broglie thought, why don't we also, in some under certain circumstances, meaning the size is very small, the particle size is getting very small, why don't we also use wave model to describe this matter, such as electron? And he's right. He's right. This idea is so important that he got Nobel Prize. Return to this formula. We don't have to go too far today. So return to this formula. What does that formula say? This formula says that if you look at if you can use the momentum to describe the particle, right? Then we can use the momentum to calculate the related wavelengths of the matter wave. Can you see that? So when we describe the electron, you can either use the momentum or the wave or matter wave. Okay. So this is let's go to next page. So this is a lot of information here, right? Today.
Yeah.
It is idea. So basically, if I return to this question, but the question is, how did de Broglie work out? How did de Broglie have work out his formula? Okay, that is the issue. De Broglie. He didn't realize he could get Nobel Prize. But how did he work out his formula? Work out his formula. It's called the matter wave wavelength formula. Do you want to know? So basic wavelength is equal to the Planck constant divided by P, right?
Yeah.
Now, first, this first equation, can we rewrite this equation as P equal to H over P, H over lambda? Can we?
Yes.
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 Yeah, of course. It's just algebra, okay? Now, then we just recall Einstein's formula, okay? To go further, we just recall Einstein's formula. So Einstein as formula for the Planck's, or also the Planck's formula, sorry, because where's the Planck's formula? Planck. Of course, Einstein uses Planck's formula too. We use Planck's formula. Formula for photon, can you see?
Yeah.
For photon energy. It's energy, okay? It's energy. And which is that the energy E, right? Not momentum, but E, the momentum equal to H multiplied frequency, all right? So that is the energy formula by Planck, right?
Yeah.
And this is frequency. If I just use the frequency, the c, light speed is also equal to lambda multiplied f, right? So therefore, the energy formula can also written as this formula, which equal to hc divided by lambda. Can you see?
Yeah.
Can you see? Lambda is the denominator. If you just rewrite this one, h multiply lambda divided by lambda multiply c. Can you see? Can you see this factor now? This cofactor, can you see? H over lambda and h over lambda. Can you see that?
Yeah.
But the only difference that is where these formulas, one formula is for the energy, another is for the momentum. Okay. Now, for the photon, the difference between the for photon, the mass for the photon, the mass is equal to 0, no mass. Do you know that? Photon have no mass, right? The mass equal to 0. Now, but we have to return to Einstein. Okay, also we have to recall Einstein's formula, which is a relativity. We call Einstein's relativity. Well, this is how de Broglie worked out his formula. Einstein. So Einstein has the formula in his relativity. Formula, sir. For the energy, for energy as mass, for energy and momentum. Here I just write down his result because you haven't seen this part, right? So Einstein says they are, so basically the total energy square will equal to P multiply C square plus M C square and square. So this is something, this is just from relativity, all right? Can we call it equation 4? This is question 4, right? Can we call this equation 5? So we're trying to figure out, or we're trying to rediscover what de Broglie has done. Okay, so this is our equation 5. Can you see? So Einstein's formula is for the particle with or without mass, all right? If we just negate the mass equal to 0 for photon, can you see? If mass equal to 0, this formula is still valid. Can you see? That will equal to P C squared. Can you see?
Yeah.
The second term vanish. Okay.
Because mass equals 0.
Yes, that's right. Or we can simply say the mass is equal to P multiplied C. Okay. Haha. Can you see that?
Yeah.
So your answer, you can answer. So we just mentioned as whose particle, which particle, his mass is equal to 0?
Photon.
Yes. So when we make this assumption, we are actually bearing in mind we are considering the photon energy formula, right? By using these formulas, we just do substitution. If we just substitute equation 6 into 4, what can we obtain? Energy became PC. Okay, E became PC. E became PC, right? Okay, you were found his formula now, and the algebra is not very complicated actually. Can you just still write this factor here, h over lambda? Can you see? That is a C. Wow. Can we simplify this formula a little bit?
PC equals PC.
No, we cancel the C. Can we? What can we obtain?
P equals H over lambda.
Wow, what is the formula? So whose formula?
De Broglie's formula.
De Broglie's formula. Actually, this is how De Broglie derived his formula, and his mathematics is worse than yours. You see, he probably haven't studied math because he was trained as a philosopher. You see, of course, his brother is a physics teacher, right? So certainly he probably learned from his brother as well. So this formula is where the Broglie start his hypothesis. You can call this can we call this question 7? Can you see? So this is how in history De Broglie make his breakthrough. Can you see? From here, De Broglie makes his formula, and he's very clever. He didn't publish this in this form, but he disguised his formula into another form. Can you see? Can you see that's right?
Yeah.
So for time being, people didn't understand how did he get this idea, as you do. Do you agree? When we see this formula, it's very strange. This formula is so strange because they combine the wave property and the matter property together, which is incredible, right?
Yeah.
So in problem solving, or you can either use his original formula, or perhaps more importantly, you could also use this formula, because this formula is exact. This relation is also exist for the photon. Can you see? Okay, now highlight all the important formula here. That is the Planck's formula, right? And this is a wave formula. So that's where when you study this chapter, that is a form you need to know. Of course, this formula you don't need to how to obtain that. Just accept. All right, that is Einstein's relativity for any formula for energy and momentum. Okay, any question? That's all for the Broglie wave.
No, not really.
Now, let's change the question. It's do you remember when did we talk about Bohr model before? Reconsidering Bohr model. Reconsidering. Bohr model. Bohr atomic model. How much do you do Bohr atomic model? Do you know how to derive Bohr atomic model?
I know that he talks about in an atom, the electrons have different sublevels, I think, of energy.
Yeah, they talk both, and yeah, basically Bohr model is about hydrogen. Can you see? So this is basically dealing with a proton and surrounded by electron. You see, surrounded by electron. You see. But unlike his predecessor, unlike people before him, he argued that for the hydrogen atom, we cannot directly use a solar system formula like Newton's law, right? We have to work out some orbital which are stable. He's called stationary. See? So in chemistry, that is the basis for chemistry, for the modern chemistry. So what he argues that Bohr model is that this is center because it's a proton, right? It's hydrogen atom. This is electron. And so basically this distance is called the radius. Can you see the shortest distance is called A? Okay. So this is the radius of each stationary. Can call this R. So this orbit called a stationary orbit. Stationary orbit, not orbital, the orbit. Okay, it's it's like the solar system, right? Now, to satisfy this condition, he argues that there's a very condition. So this is to say the moment, he says angular momentum L or the P multiplies R equal to mass RV, right? Must equal to, very strangely, must equal to Planck constant divided by 2 pi. Have you studied this formula before?
No.
Did your teacher mention that?
I think so.
You think so? So, or another thing, I have put this have another integer here. This integer, can you see? So n is equal to 1, 2, 3, and so is a positive integer from 1, right? So this formula is called Bohr quantum condition. It's Bohr, yeah, in your textbook you can see that because the quantum condition. Quantum condition. Okay. So this is a formula in addition to Newton's law. Bohr introduces a quantum condition. Okay. So as a result, Bohr worked out the two formulas. One is for the radius. Okay. We put the sub n represent a different shell or different orbit. A multiplied n squared. Another formula for the energy. Yes, you can draw the energy level based on second formula. That's 13.6 n squared. Okay. So in these two formula, n is equal to, as this, actually he derived his formula based on this assumption, 1, 2, 1, 2, 3, and so on. Can you see? So in chemistry, we know that this the first shell can hold up to 2 electrons, right? And the second shell can hold up to 8. So this is n equal to 1, and is n equal to 2. Okay. And then what is A? A is called the Bohr radius. So that is the Bohr radius, which is equal to the 10. That is the size of the hydrogen atom, the radius. That's 10 to the power negative 10 meters, right? Oh, by the way, that also use unit. If you use Armstrong, that's the old unit for the wavelength. So
now nanometers, right?
It's not nanometer. So 1 Armstrong, this Armstrong's one, this called this unit. This one is called 1 Armstrong. Swedish, the Swedish, and he. So actually, they have this. They have this notation here. Can you see? Not English. It's called Armstrong. 1 Armstrong is equal to this number. Can you see? Equal to 10 to the power of 10. Can you see? But 1 nanometer is equal to 10 to power 9, -9, different. Can you see?
Yeah.
All right. Anyway, so that is how Bohr derived his formula. But Bohr just assumed this is their assumption, right? He just assumed this formula must be hold. But after we have studied the Broglie wave, perhaps you can rewrite this formula a little bit. Can you see? Can we rewrite this formula? So that is mv multiply r, right? Equal to n Planck constant divided by 2 pi. Can we multiply 2 pi on both sides? We got 2 pi r, can you see? 2 pi r multiply p equal to Planck integer, okay? Can you follow me from here to here?
Yeah.
Then can we just do some substitution? The formula we just used. P equal to what? According to Broglie.
H over lambda.
Yes. Can you tell me? Can you write down your result here? If we combine this formula, sub this formula into this formula, can you see? Into this Broglie formula, what can we obtain? Yes, can you simplify that? Yes. Yes, that's right. So this is actually Bohr's formula in terms of the Broglie wavelengths.
Yeah.
In other words, can you see what is this? Can you see this circumference of a circle? Can you see that? 2 pi r is circumference, right? If we just use it's hard to draw with circle. If I just redraw this circumference as a blue light, can you see? This is C, you agree? So this represents the C. So this is 2 pi r, can you see? Circumference equal to circumference. So what does that mean? When n equal to 1, we will have a sine wave, just one sine wave. Can you see that? If I draw this wave, so it's halfway here. That is first, it's called a fundamental harmonic. You remember? As n equal to 1. How about n equal to 2? N equal to 2, we got the 4 sine wave. Can you? 2 was 2 sine wavelengths. Can you see? There's one, another one, and another one. Can you see? So this is n equal to 2. So when the Broglie wavelength is fixed, and then this harmonic just multiple of the Broglie wavelengths. Can you see? So in the first place, this one Broglie wavelength. Can you see? Can you see? And then, this is lambda 1. Okay, lambda 1. This is lambda 2, right?
Yeah.
This is lambda 2. What is the phenomena? Do you remember in when we studied do you remember standing wave? No. Anyway, if this is just the different interpretation. So if you want to know more, you have to review the standing wave. Okay, what is a standing wave? Standing. We have studied standing wave before, like a string in the fixed. Do you remember when we studied a string in the 2 fixed part? To see that how many harmonicas it can generate. Do you remember this formula? Have you do we study this before? Standing wave. Probably you forgot, all right? Anyway, that is how we apply the Broglie formula. So that is how we can use the Broglie's formula to explain why Bohr makes such assumption. Okay. But unfortunately, Bohr didn't know why he did so. He just worked out what he want. But it is de Broglie 2 years later. So the Bohr put his model in 2 years before. That is that was 1923. All right. Okay. That is a related knowledge and historical background.
Yeah.
Okay. Any question?
No.
Okay.
So we like electrons travel as waves as well.
No, electron can be described by electron can either be described as a particle or a matter wave. When you describe electron as a wave, forget about the particle property. All right. Otherwise you cannot explain this experiment. You see.
Yeah.
So this table tell you everything. Think about it, right? So think about the basic idea in methodology in physics. We never use real stuff. We use models all the time, okay? Although these two models are not compatible, okay? In the early days, people trying to make this model interpretation compatible. So they invented many ideas such as duality. You have heard of duality, which means that the electron is with property of the wave and the particle at the same time, like personality. What is bipolar in psychology? What is terminology? Different personality. Bipolar means two, right?
Yeah.
Anyway, did I answer your question?
Yes.
Okay, let's stop here and think about it. We can continue discussing. Okay, next time. Okay, goodbye.
Thank you. Goodbye.
See you next time.